Greetings, I'm Professor Sever. In our linear algebra notes for today, we're going to investigate coordinate systems. So first, let's review or present for the first time, if you haven't seen it, a very important theorem. It's called the unique representation theorem. So if S is a basis for a vector space V, and here we see S has n vectors in it, therefore V is finite dimensional, namely the dimension of V is n, then in this case we can write any vector in the vector space V uniquely as a linear combination of the elements in S. And when we say unique representation, what we mean is it's not unique in terms of the order that the vectors are written in, because of commutativity we could commute these two vectors and write the first two elements of this linear combination as C2V2 plus C1V1. But what we mean is it's unique in terms of the coefficients, the weights. There's only one number you can multiply V2 by, etc. There's only one number you can multiply Vn by, namely Cn, and add those results to get the vector V. If any of these coefficients were changed, then it would produce a different vector V. So unique representation. Now what this theorem says, it really brings together two important things. Since the span of S is V, we know that every vector in V can be written as a linear combination of these vectors. That's what the span does for us. That gives us the existence of the C's, the C1, C2, up to Cn. The independence gives us the uniqueness, the unique representation for that linear combination. Let's look at the definition of coordinates in a finite dimensional vector space setting. So now we have a basis B, V1 through Vn. So of course that would say, again, V is finite dimensional with dimension n. Unique representation, a vector V in the capital V, the vector space V. Then it can be written uniquely as follows in terms of the basis elements. So now, this expression of V in terms of those basis elements produces unique scalars. That's unique representation. Those scalars are called the coordinates of the vector V relative to the basis B. Now, and this next part is not fleshed out in some of the undergraduate or sophomore level texts, but if we consider B to be an ordered basis, now we know we have a set here, we've written B as a set. Sets aren't inherently ordered, and there are different notations that one may use for ordered bases. Sometimes we use a pointy bracket here and here to indicate that it's ordered, but what we mean by ordered is that V1 is the first vector, V2 is the second, up to, and Vn is the last. Again, technically you would need a function that assigns to the number 1, V1, assigns to the number 2, V2. So in other words, we're looking at this as more of an n-tuple or a sequence, an ordered sequence. So once you have an order, again, why is order important? Because of commutativity. We can commute the order of any of the two summands in any sum of two vectors. So again, if B is ordered, then what happens is we can say C1 is the first coefficient, C2 is the second coefficient, C3 would be the third, and so on, and finally Cn would be the final or last coefficient. And once we do that, in essence, we construct a column vector in Rn that's associated with those weights. In fact, we will go further and say that this column vector is the coordinate vector of that vector V relative to this ordered basis. And here is our notation, and this notation here on the left-hand side of the equal, the bracket subscripted by the basis, is read as the coordinate vector of V relative to the ordered basis B. And again, that's a column vector in Rn. What this does, this allows us in an abstract vector space V to take an arbitrary vector. Once we have it written as a linear combination of an ordered basis, we can convert it through this process of coordinates into a column vector. The abstract is represented by the concrete. Let's look at an example. Example 1. Suppose V is P2. Remember, this is the polynomial space of degree 2 or less, including the zero vector, the zero polynomial. And now we have two different bases. And notice they're the same elements. And notice we have two different ordered bases. B1 and B2 are the same set. They have the same elements. But if we say they're ordered bases, well then the first element of B1 is t squared. In contrast, the first element of B2 is the number 1. Okay, so you can see the order has just been switched. We've just reversed these from first, second to third. We've constructed B2 in the reverse fashion. And we do this to illustrate the importance of the order and what it does for coordinates. So let's take a vector, particular vector P in P2, t, which is 2t squared plus 5t minus 6. What are the coordinates with respect to both of these two bases? With respect to B1, the coordinates are, in order, 2, 5, and minus 6, and those are written here. 2, first element, corresponding to the first vector. 5, second element, corresponding to the coefficient of the second vector. Minus 6, third element, corresponding to the third element of the vector. Now remember, this is technically negative 6 times 1, or plus negative 6 times 1, this element. That is not written here, but that's why this becomes a negative 6. Thus, the coordinate vector of 2t squared plus 5t minus 6 with respect to B1 is the column vector 2, 5, minus 6. Similarly, the coordinate vector of the same vector P with respect to B2, and since the vectors are reversed here, we'll see that the coordinates are also reversed. So it should be minus 6 times 1 gives us the first element of minus 6. 5 times the second element t gives us 5. The second element of t is here, gives us 5 in the second entry of the coordinate vector. And then 2t squared is 2 times the third element of t squared. This gives us a 2 in the third entry of our coordinate vector. Okay, so in this previous example, we found those coordinates quite easily. Well, why? Because this was a very nice basis to work with. We call that basis B the canonical basis, that basis of 1t and t squared, the canonical basis of P2t. So we didn't really have to make any computation. We found those coordinates by inspection. Sometimes you'll have to make computations. In fact, most of the times you will have to make computations. Thank you for watching this introductory video on coordinates in linear algebra. I'm Professor Sever. Thank you.